What actually happens when artificial intelligence steps out of the computer monitor and picks up a paddle to play elite table tennis? For decades, AI has operated entirely in the digital world. It easily mastered the pristine, mathematical environments of chess and Go, but it always struggled the moment it had to deal with the messy reality of gravity, friction, and fast-moving physics. We have robots that can run a marathon, but running is a rhythmic, highly predictable action. Ping pong is the exact opposite. It is pure, chaotic reactivity, requiring split-second decisions against high-speed volleys. Defeating a world-class athlete in a game defined by split-second reactions forces AI to solve the friction and gravity of the real world, challenges that simply don't exist behind a screen. Sony built a machine to take on that challenge. They call it ACE. It doesn't have eyes or legs, but instead relies entirely on a single 8-jointed mechanical arm to navigate the table. To see the game, 9 high-speed cameras surround the court. They track the tiny printed logo on the table tennis ball, calculating its exact speed and spin in milliseconds. Because a mechanical system can move far faster than human biology allows, the researchers intentionally handicapped the robot. They capped its maximum reach and speed to perfectly match a skilled human who trains roughly 20 hours a week. By imposing those strict physical limits, Sony ensured the match wouldn't be won through raw mechanical speed. It became a test of tactics and AI decision-making against human intuition. You cannot write a few lines of code to teach a machine how to play a sport like this. The physics are far too complex to map out manually. A robot has to learn through trial and error. To pull this off, the engineers used an AI method called reinforcement learning, forcing the system to develop a physical intuition for the game by rewarding it for good returns and penalizing it for misses. ACE spent 3,000 hours playing simulated matches. It failed endlessly in the digital space, attempting thousands of bad swings until the exact mechanics of a successful volley were perfectly mapped out in its system. That massive volume of digital simulation gave the robot the ability to accurately anticipate the unpredictable real-world bounces of a plastic ball. The results of that training were put to the test on an Olympic-sized court. ACE secured 3 distinct wins against high-level amateurs, though it struggled to take more than a single game from the top-tier professionals. This bar chart shows exactly where the robot excels. Faced with intensely spinning serves, ACE returned 75% of the balls, a rate few amateurs can replicate. But human players found a vulnerability. When hitting a simple knuckle serve, the machine's success rate plummeted. Figuring out those mechanical blind spots was crucial for the human athletes, who reported that playing ACE is deeply unsettling. There is no heavy breathing, absolutely no hesitation, and no readable body language to clue you in on its next move. The humans exposed a fascinating flaw. ACE possesses superhuman calculation for intricate problems, but it severely over-engineers its responses to easy ones, lacking the common sense a human player uses by default. ACE's presence at the table suggests that AI is no longer a disembodied brain. It is starting to occupy the same physical space we do. If a machine can perceive an object, reason through its physics, and physically act on that information in milliseconds, it has the baseline tools needed to navigate unstructured human environments. The technology driving ACE's paddle will likely migrate from the court to active factory floors, fast-paced hospital rooms, and eventually into humanoid robots. Skeptics rightly point out that a ping pong table is still a highly controlled arena. The robot can see everything clearly, and it doesn't have to navigate the severe physical dangers or the vague, messy context of an open city street. While the knuckle serve proves ACE still lacks basic human intuition, the speed of its learning is significant. Researchers predict that as these systems learn to handle the simple unpredictability of daily life, physical robotics will undergo a surge in capability, similar to the sudden rise of generative AI. If you are stepping up to the table against ACE, what specific serve would you use to break the machine's logic? Let us know your strategy in the comments below, and make sure to subscribe for more deep dives into the future of robotics.